Hello, everybody. It's Mrs. Crumbliss. Um, Here are your notes on 5.2 and 5.3. There's also a simulation on nuclear decay that you need to work on in Schoology. It's you go to an online website, you pull up a dice app, you roll some dice, gather some data, make some graphs, and it helps you look at nuclear decay. Please make sure that you are keeping up on your work and getting things turned in as we move through this unit. Um, and remember that the AHP is going to be due on the 21st and 22nd. If I feel like I need to move that date, I will. But at this point, we're just going to leave it where it is. All right, so let's go ahead and get started. We are going to start with our warm up. If you want to pause the video and go ahead and read through the warm up to see where we're at and then try to answer it, that's totally fine. If you want to just skip through and see what the answer is, that is also fine. So it says the gas phase reaction of A and B, giving me 2AB, is assumed to occur in a single step. The two experiments are done at the same temperature inside rigid containers. The initial partial pressure of A and B in experiment 1 is twice the initial pressure used in experiment 2. Which statement provides the best comparison of the initial rates of formation of A, B in experiments 1 and 2? So while A is correct that we are at the same initial temperature, because the pressures are different, the collisions will not be the same. So we know A is not correct. The initial formation of AB is slower in experiment 1 than experiment 2 because they're at the same pressure. B is not correct. That higher pressure isn't going to reduce the volume because we are in a rigid container, meaning the volume can't be reduced. Initial rate of formation of AB is faster in experiment 1 than experiment 2 because the pressure of the collisions between A and B molecules would be more frequent, increasing the probability of successful collisions. And C is going to be our correct answer because the higher pressure does lead to more frequent probability of successful collisions. D says the initial rate of formation is faster in 1 than 2 because the higher pressure, a larger fraction will have the minimum energy to overcome the activation energy. The larger pressure doesn't really change our energy, it just changes frequency. So that right answer is going to be C. For question number 2, it says the proposed rate determining step for the reaction is 2N2 plus, 2 nitrogen dioxide is going to yield nitrogen trioxide and nitrogen monoxide. The graph shows the distribution of energies for nitrogen dioxide molecules at 2 temperatures. Based on the graph, which of the following statements best explains why the rates of disappearance of nitrogen dioxide is different at temperature 2 than temperature 1? A says nitrogen dioxide is consumed at a faster rate at temperature 2 because more molecules possess energies at or above the minimum required collisions to lead to the reaction compared to temperature 1. Okay, so it's not a bad answer. I'm going to underline it and circle back. Nitrogen dioxide is consumed at a faster rate at temperature 2 because the molecules have a wider range of energies, allowing for better orientation during the collisions compared to temperature 1. That one's not right because the energy here at the end is the same. So it's not giving us a wider range of energies. The range of energies is the same. Fewer nitrogen dioxide molecules have relatively high energy at temperature 1, which favors collisions rather than between molecules in the container, leading to faster disappearance. No, that one just doesn't make any sense. Nitrogen dioxide molecules have a relatively low energy at temperature 1, which increases the number of effective collisions taking place and the rate of disappearance compared to, no, it does not do that. So A is our best answer. So let's go ahead and start talking about rate laws and changes of concentration over time. So if we read through this question carefully, we see it's a Maxwell-Boltzmann type distribution. A is going to be our best answer due to just the fact that there's the same amount of energy distribution regardless, because the beginning and end energies don't change. All right, so let's get into kinetics for today. We're going to talk about the introduction of rate laws and concentration changes over time. So rate law. So this is different, or reaction rate. So this is what we were working on last class. Reaction rate reports the average rate over a period of time. Or an instantaneous rate at a specific time. But what we're going to get to in this section is actually rate law. And rate law is different in that this is a mathematical relationship between the rate and the concentration of species in solution. So this is gonna not be quite the same. There can also be a differential rate law, which our differential rate law is the change in reactant as a function of time. Oh, functions, I know you're excited. And then we have the integrated rate law, which is the actual concentration of reactants or products as a function of time. And for the most part, these are like equations given to you. Like you're not going to have to, like, there's a lot of information for this given to you on your equation sheet. So this isn't a bunch of stuff to memorize. This is all pretty much provided for you on your equation sheet. So rate laws must be determined experimentally. We are not using the coefficients. Our rate laws are going to look like this. Rate equals K, the concentration of reactant 1 to the M times reactant 2 to the N. M and N are typically small whole numbers. And then K is this rate constant. And so this is something that we will either be given or we'll be able to calculate. K is the proportionality between the reaction rate and reactant concentration. K changes with temperature. So anytime there's a temperature change, K has to be recalculated. So if we look at what we just looked at, so the exponents tell us the reaction order with respect to each reaction. So we can say that with respect to ammonium, our reaction is first order. With respect to the nitrite ion, the reaction is first order. And then if we want to know the overall reaction order, that's going to be the reaction order of each reactant. So I have an overall reaction order of 2. So if we look at some of the examples down here in our table, here we have a reactant that's first order, a reactant that's first order. So my overall reaction order is 2. Here we only have one reactant, it's first order, so my reaction order is 1. Again, one reactant, reaction order 1. Here's a weird one where we have a reaction order of 1 and a reaction order of a half. So my overall reaction order is 1.5. And this is just about adding together those exponents to get an overall reaction order. So how do we know which reaction order is which? What are we really looking for? So when we're looking at reaction orders, something is a first order reaction if the concentration doubles and the rate change doubles. It's a second order reaction if the concentration doubles, but the rate order quadruples. So it changes by 4. It's a third order reaction if my concentration doubles, but my rate change increases by 9. So you just kind of have to get used to looking for, is the rate going to double? Is the rate going to triple? Is the rate going to increase by 9? First order, second order, third order. And then this just gives us some examples of what our different rate laws might look like and what our units are for the rate laws. So it's important to be able to recognize the units for K, because if you can recognize the units for K, a lot of times you can use that to figure out the rate order, which helps you know which integrated rate law to use, or it helps you use the integrated rate law properly. So if I have something that's 0 order, my units for K are going to be m to the s minus 1, and our rate law is going to look like K concentration of A to the 0. Reaction order of 1 is to this per second, and it's going to look like K concentration of A. Reaction order 2 can look a couple different ways. Its units are going to be per molarity per second, but we can either have one reactant that has a rate order of 2, or we can have 2 reactants that we add together. And then if we have a rate order of 3, it's going to be per molarity squared seconds squared. And again, we can have 1, 2, or 3 reactants on a third order rate reaction. These third order ones are pretty rare. We don't see them very often. Most of our stuff is first order with some second order in there. Third order is pretty unusual for us. The rate constant can be used to estimate the relative rate of the reaction. If K is times 10 to the 9 or higher, the reaction is considered fast. If K is 10 to the 9 or lower, the reaction is considered slow. So this K value helps us to understand what is fast and what is slow in our different reactions. All right, so let's turn to in-class practice number 5 and actually practice doing this a little bit. So here we have nitrogen monoxide gas is a product of the reaction. Actually, the reaction's below, not above. It lies. Can react with oxygen to produce nitrogen dioxide gas, as represented below. The rate study of the reaction yielded the data recorded in the table. So there's our data table. Determine the order of reaction with respect to each of the reactants. Give a reasoning. Give reasoning, clearly explain, and showing how you arrived at your answer. So if I look at N and O, I want to find a place where N and O changes, but O2 stays the same. So I am going to look in this case at reaction experiment 1 and experiment 3. So when I look at experiment 1 and 3, the concentration of nitrogen monoxide triples and the rate changes by 9. Because 1 triples and the 1 changes by 9, this is going to be a second order with respect to the concentration of nitrogen monoxide. So I would write that as NO2. If I look at, I'm going to go ahead and erase these 2 highlights. If I look at my rate with respect to oxygen, I'm going to want to look at experiments 1 and 2. And when I look at experiments 1 and 2, the concentration of the oxygen triples and the rate triples. So this makes that one first order with respect to concentration of O2 to the 1, because they're directly related. It's a 1-to-1 ratio, so it's a rate order of 1. If I move on to B, which asks me to write the rate law, remember our rate law includes K, so this is going to be rate is equal to K, concentration of nitrogen monoxide to the second power, concentration of oxygen. And then if we move on to C, C asks us to determine the rate value for the reaction, for the rate constant for the reaction, clearly stating its units. So here I'm going to solve for K, and I just want to pick any experiment. So I'm going to pick experiment 1. K is going to be equal to 8.52 times 10 to the negative 2 molarity per second. My concentration of nitrogen monoxide squared, which has a unit of molarity, which is also going to be squared. And then my concentration of oxygen, which just has a unit of molarity. And once I put this all in my calculator, I get 7100000, or 7.1 times 10 to the 6. And this is going to be meters per meter squared per second. This meter and this meter are going to cancel. So there's one example of how to solve these problems. Now let's look at problem 6. And this is another one where we're just going to determine the reaction order. So the reaction order for, and notice that this one is a gas. So here we're looking at pressures. We're not looking at concentrations. So remember we talked about last class how sometimes pressure and if we're talking about gases, we'll talk about pressure. If we're talking about aqueous, we'll talk about concentrations. So I'm going to look at this with respect to the pressure of nitrogen monoxide. I'm going to look at experiment 3 and 4. So if we look at 3 and 4, nitrogen monoxide doubles, but hydrogen stays constant. And my rate on this one quadruples. So the pressure of nitrogen monoxide doubles, the rate quadruples. So this is second order with respect to the pressure of NO, and I'm going to write that as PNO second power. Notice that we don't put these in brackets because they're not concentrations, they're pressures. So then if I'm looking at pressure and hydrogen, let me change the color. I'm going to look at experiments 1 and 2. For experiments 1 and 2, the pressure of the hydrogen gas doubles, the rate doubles. So this is first order with respect to the pressure of hydrogen. And so that's going to be just written with parentheses around it. So if we look at B asks us to determine the overall rate order, but I think it makes more sense to write the rate first. So we're going to write the rate first. So we're going to go to C. Rate is going to be equal to K, the pressure of nitrogen monoxide to the second power, the pressure of hydrogen to the first power. And remember, to figure out my overall rate order, I'm just going to add those powers together. So my overall rate order is 3. And then for D, I'm just going to use reaction 1, 0.66 millimeters of mercury per second. My pressure of nitrogen monoxide squared, millimeters of mercury squared, pressure of oxygen, millimeters of mercury. And of course, when I worked this problem earlier, I never gave it any answer. I got 5.625 times 10 to the negative 4. And my units are going to be millimeters of mercury per millimeters of mercury squared seconds squared. All right, I should have calculated it before I recorded it, but I fixed it. So redoing my math, I end up getting 2.75 times 10 to the negative 8, but my units don't change. These next few slides are kind of just an idea of what the different graphs are going to look like for each order of reaction and the integrated rate law and looking at the units. So a lot of this is just to take in. You should have a sheet of paper that the sub gave you where you can write this down and the graphs are there for you, so you don't have to redraw the graphs. So make sure that you find that piece of paper. So if we have a zero order reaction, the rate is independent of concentration. It doesn't matter what the concentration is. I'm going to have a flat slope if I graph rate versus concentration. So the graph of the concentration versus time is straight with a slope of negative k. So if I am going to look at my integrated rate law, I'm going to have the concentration at time t minus the concentration initial is going to be negative k to the t. And my units for this are going to be meter or molarity per second. Remember that our rate of reaction depends on concentration. K does not. So K is affected by temperature and catalyst. So they just have different things that impact them. If I look at my first order reactions, the rate is directly proportional to the concentration of one reactant. And here, if I have the concentration over time, it's going to give me a slope, curved slope parabola, I think is the word I'm looking for. But if I do the natural log versus time, I get a slope of negative k. Here is my integrated rate law in slope-intercept form. This is given to you on your equation sheet. So the integrated rate laws are given on the equation sheet. You don't have to memorize those. Here's the integrated rate law as we typically use it. But here is what it looks like on the equation sheet. So realize that the equation sheet and what we look at can be different. We don't need to know how to derive the integrated rate law. You just need to know how to plug things into it. So we're going to use it, but we're not going to derive it. It's important to be able to recognize the graphs because sometimes they're just going to give you graphs and you're going to have to decide what order is this reaction just by the graphs I'm looking at. So in this case, the graph of 1 over the concentration per time is going to give you the most linear graph, and that tells you that it's a second order reaction. And then here's the three graphs that we use most. Realizing that your first order reaction This is your most linear graph, or zero order, set first order reaction. This is your most linear graph. Second order reaction, this is your most linear graph. You are going to need to be able to look at the graphs and recognize what is the most linear graph and what order that means the reaction is. So let's go ahead and grab our in-class practice, look at question 7. And this gives us a set of data and asks us to determine the reaction order and calculate the value for K. So what I need to do on this is I need to plot this data, and I need to plot it to find the most linear fit. So if I plot this data as concentration versus time, and you can do this on Desmos, you can do it on one of the TI-83 calculators. But if I do it as concentration over time, I get a graph that looks like this. If I do it natural log concentration versus time, I get a graph that looks like this. If I have 1 over concentration versus time, I get a graph that looks like this. So because the natural log of concentration versus time is my most linear, therefore the reaction is first order. I can then get the slope of the line from my graph. Not line. I don't want the slope of a line. To get K, because negative K is the slope of the line. So K is going to equal 3.15 times 10 to the negative 3. And I just got that from the graph that I made. So make sure you know how to graph the data. I will not make you graph the data on a test. If I want you to do this, I will just give you the graphs and have you identify. So don't feel like you need to be able to graph on the calculator or make these graphs quickly. That's not the point. All right, so let's look at number 8. Number 8 says dinitrogen pentoxide is an unstable anhydride of nitric acid that decomposes by first order kinetics into nitrogen dioxide and oxygen gas as shown below. The rate constant for this reaction is there. So I know K. The initial concentration of dinitrogen pentoxide is this molarity. How long will it take the concentration to drop to 0.5? So I know that this is a first order. So because it's a first order, I can use natural log the concentration of my dinitrogen pentoxide at time t minus the natural log the concentration of dinitrogen pentoxide at the initial time is equal to negative KT. I'm going to solve for T. And when I plug all those numbers in, I'm going to use the natural log of 0.05 minus natural log of 0.5 divided by K. And my time is going to equal 3,701 seconds. It's weird that it's in seconds, but it's fine. If I look at B, it says to take the same reaction, but it was carried out at a different temperature. What is the new rate constant? If the initial concentration is this, after this many seconds, and the other concentration is 0.2 molar. So here I'm again solving for K. I'm still using the same natural log rate law, integrated rate law, because it's still a second order reaction or first order reaction. Natural law. But now it's over negative T. And there is my new K because my K has to change if my temperature changes. Please make sure you ask me any questions you have about anything in here. I will answer those questions in the Schoology assignment just like I did for the last time that we did this for block 3. Block 5, I know this is new for you. We only have one set of notes that I will give you left, and I'll be back soon. Miss y'all. See you then.